All right, welcome to Physics Video 4.2. We're going to learn today about centripetal force. Please excuse my sniffling as I sniffle my way through the video here. All right, so here's the objectives for today. Take a second, read through them, write them down. All right, I'm going to assume you've done that. All right, so at the end of the last example, we were talking, or at the end of the last video, I'm sorry, we were talking about Buzzy the bee. He was spinning around in a circle. His radius was 0.75 meters, and he had completed 10 revolutions in 8 seconds. If you've not yet watched that video, you absolutely have to go back and watch it before you watch this one, or you're going to have no idea what's going on. All right. So based on that information that we calculated, we were able to, that we measured, we were able to calculate the period, the frequency, and then using either of those, we were able to figure out, using this equation, sorry, I probably should have boxed in the v there, or this equation, we were able to come up with the fact that the velocity for the bee, as he traveled around in the circle, tangential velocity, was 5.89 meters a second. All right, we're going to sort of learn more about the bee today. All right, so now that we've talked about describing circular motion, we need to talk about why objects travel in a circle. In other words, we learned for the bee to sort of talk about what he's doing while he goes in a circle, how fast he's going, how often he goes around, how long it takes him to go around, but we haven't talked about why he goes in a circle. All right, so here's what we know about any object that goes in a circle. We know that any object that's moving in a circle is always changing direction. That means that if it's changing direction, remember that means the velocity is changing, right? Because velocity includes speed and direction. And since the velocity is changing, you're accelerating. So any object going in a circle is accelerating. And the name of the acceleration that the object experiences while it goes in a circle is centripetal acceleration. Centripetal acceleration. Okay, say that word once. All right. The Greek root of it, if you care, means center seeking. Centripetal. Centripetal. All right. So what that is the acceleration that an object experiences due to the change in direction required to go in a circle. So any object that's going in a circle is accelerating. The name of the acceleration just from the change in direction is called centripetal acceleration. And here's how you calculate it. Centripetal acceleration is v squared divided by radius. And notice, the bigger your velocity is, the bigger your acceleration is, right? Which should make a little bit of sense, because if you're driving around a corner, the faster you're going, the quicker your direction is changing, right? And similarly, the smaller your radius, the bigger your acceleration is, right? Because if you turn on a really tight corner, you're asking your velocity to change very quickly. You're asking the direction to change very quickly. All right? Now, deriving that equation, down here at the bottom it says this, deriving that equation, oh man, sorry. Deriving this equation requires a fair amount of geometry and algebra. But if you're interested, I'm totally happy to show you the math, just not right now. So ask me before or after class sometime, and I'm happy to show you. All right, I'm sparing the 99% of you that don't care. If you cared, you would have taken honors physics. So there you go. All right, so Newton's first law tells us that there must be a force causing the object to accelerate, right? Remember, we're going in a circle, we're changing direction, the velocity is changing, so we're accelerating. That requires a force, okay? And the name of the force that causes something to go in a circle is centripetal force, okay? Centripetal force is the name of the force that causes an object to change direction so that it can go in a circle. And so the equation should look fairly obvious, right? It's mass times acceleration. Centripetal force is the mass times the centripetal acceleration you want, okay? Now, since, as we learned in the last video, centripetal acceleration is v squared over r, you can substitute this, in there to get this. So more often than not, I will use this equation to find centripetal force. Occasionally, though, if I already know the acceleration, then I'll use that guy. Okay? So let's do a quick numeric example. So back to Buzzy the bee. Suppose his mass had been 0.25 kilograms. If I asked you to find his acceleration, what would we do? So take a second, pause the video, see if you can do it. Cool. So to find the acceleration, it's v squared over r. Remember, his velocity, we figured it out last time, and I wrote it at the beginning of this video, was 5.89 meters a second. We're going to square that number and divide it by the bee's radius. The radius of the bee's circle. Be a big B. And so the answer we get is 46.3. Oh, shoot. 46.3 meters per second squared. And the units do work, right? You're going to have meters squared per second squared divided by meters gives us our acceleration units. All right? And then to find the centripetal force, since I already know the acceleration, I'm going to use this guy. So I'm going to multiply the mass of the B by his acceleration and get 11.6 newtons. Okay, so there's the centripetal force on the B. That's how much force is required to keep the B going in a circle. Okay, so what I tend to find is people don't, in this chapter, don't have a tough time with the math. It's basically, like it says here on the screen, basically just chug and chug. The tough part is identifying what the centripetal force is, not numerically, but conceptually. What is that number we just found? This, what was it, 11.6 newtons? What does that represent? He's going in a circle. There's a force keeping him going in a circle. That's how much force is required. Well, where's it coming from? Well, let's think about it. So Buzzy's going around and around in a circle, right? So this circle here represents the path that he's following, right? So he's going around and around and around like this, around and around, right? Okay. So these arrows represent the velocity, the direction that he's traveling at any given instant. It's a sort of a velocity vector, okay? So the idea is when the B is right here, he's traveling this way, right? Now think about Newton's first law. Newton's first law says if there's no force on an object, the velocity is going to be constant. So if there's no force on the B, his velocity would stay constant. He would just keep going this way forever, right? And as he did that, he would be getting farther and farther away from the center of the circle, wouldn't he? So he would be sort of escaping away from the center, right? But there's a centripetal force. Remember, centripetal means center seeking. Force forcing him back towards the center of the circle to keep him on his circular path, right? So now the B has been pushed or pulled inward, so now he's here. Now he's going this way, right? If there was no force on him, he would move away from the center of the circle. But he doesn't, or he can't, in fact, because something is pushing or pulling him inward towards the center of the circle. So now the B is here, right? Remember, the B always stays on the red path. And as much as he wants to go this way, there's always something pushing or pulling him inwards, keeping him on the circular path. Okay? So down here, it basically explains that. Let's see, down at the bottom of the screen now, says, so if there's no force on him, Buzzy would get farther and farther away from the center of the circle. So there must be a force pushing or pulling him inward. Inward, that word is super, super important. Okay? There must be a force pushing or pulling him inward. The name of that force is the centripetal force. That's what that 11.6 newtons was. It was the inward force that prevented him from going flying outwards. Okay? So the centripetal force always, 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 always pushes or pulls the object inward toward the center of the circular path. All right? But we still haven't identified what it is. What we know now is that the B is going in a circle. We know something is pushing or pulling him inwards. We don't know what it is. So at this point, visualize it. You're the B spinning in a circle, right? So when the B got to here, for example, he wanted to keep going this way. Well, why didn't he? Well, he's attached to a rope, right? There's a string tied to him. The string was 0.75 meters long, right? And string is sort of not stretchy, right? I mean, technically it stretches a little bit, but... and so the idea is the B can't possibly be more than 0.75 meters away from my hand, right? And so the idea is, as much as the B wants to go this way, to do that, he would have to get more than 0.75 meters away from my hand. He can't do that because the string is restricting his movement, so the string must be forcing him, pulling him inwards. All right? So all of these forces represent our centripetal force. It's always pulling him inwards. It is crucial that you're able to describe the centripetal force, and that's what the rest of this video is going to be about. You have to be able to describe the centripetal force as well as calculate it. All right, so to get you started, we're going to do some examples here, but here's one to get you example. For Buzz, or here's one to get you started. For Buzzy the B, the centripetal force was this. The string pulls Buzzy the bee inward. Okay, 4 parts to that. Okay, you have to identify all 4 parts. Okay, you got to tell me what's doing the pushing or pulling. You got to tell me if it's pushing or pulling. You got to tell me what's being pushed or pulled. That's always the object going in a circle. And you got to tell me which way it's being pushed or pulled, which will always be inward. Okay? So, this is a little bit tough to see because when I'm spinning the bee around, you can't really see me pulling him inwards. You can't see me pulling on the string. So we're going to do some examples. I love this first example. All right, it's called the hammer throw.
Okay, so the hammer throw, this originally was an old Olympic sport, right? And they would take literally a giant, Thor-like hammer at the end of a chain, and they'd spin it around and try to throw it as far as they could. So, but before they throw it, what they do is they spin around like this to kind of get the hammer moving, and then they release it, okay? Now here they're using a giant lead ball instead of a hammer, but it's the same idea. What I want you to do is I want you to watch while these dudes are spinning around. That lead ball you can see there at the end, it weighs, I don't know, I want to say it's like 5 to 8 pounds or something like that. They're pretty heavy. But see how he's pulling in right there? You can actually see him pulling inward to prevent the ball from going flying outward, okay? Let me see if I can pause it at the right minute. Okay, do you see? So right now, he's pulling inward because the ball is over here. The ball wants to go in a straight line, and he's trying to prevent that from happening. So to change the velocity of the ball wants to go this way, he needs to pull inward to prevent the ball from going in a straight line, okay? This is totally worth watching again. You might want to rewind and watch this a couple times because this is a great example of centripetal force. You can really see the centripetal force here is the person pulling the ball or the person pulling the chain inward. I guess technically we would say the tension pulls the ball inward, but the reason that tension is there is because the person is pulling the chain, right? Okay, so there you go.
So, if you need to, you might need to, oops, I spelled hammer wrong. You might want to rewind a second. I want you to watch that again, what you just saw. Rewind. Okay, what he's doing is he's spinning around a ball that's a lead ball at the end of the chain. In the olden days, it used to be literally a hammer, which is why it's called the hammer throw. But he's literally leaning back, pulling that ball. It's like an 8-pound ball, Picture putting a bowling ball at the end of a chain and spinning it around, okay? So you literally see him pulling it inwards and then releasing it. When he releases it, it goes in a straight line, right? Because there's no centripetal force on it, okay? But while he's spinning around, before he throws the ball, the centripetal force is the athlete pulls the hammer inward. Or you could say the athlete pulls the chain inward, or the chain pulls the hammer inward, or whatever. But there's an inward force on that hammer, or on the ball at the end of the chain, that keeps it going in a circle. And again, when he lets go of the chain, lets go of the ball, that's when there's no centripetal force, and then you can see it goes off in a straight line, right? Okay? All right, the next one is called the rotor.
Lancement imminent.
That's an old amusement park ride. So what's happening there, that giant tin can is spinning around and around with people inside it. And so in that example, the walls of the ride are pushing the people inward, right? Look, it's this. Here's your person, right? Right now he's going this way, right? He wants to keep going that way, but he can't because the walls of the ride are pushing him inwards, right? Okay, salad spinner is basically the same thing. Watch the water in this video here.
We're here to demonstrate the incredible simplicity and capability of the new Xylus Easy Spin salad spinner. Here's how it works. First, remove the lid. Inside, you'll find a basket with an interior that's so smooth it keeps fruits and vegetables from bruising. Next, pour the salad into the basket, which also doubles as a colander. Now place the basket into the bowl and secure the cover. Now you're ready to pull the handle and spin that salad. Your salad is spun clean at over 1800 RPM. And with its non-slip rubber base, the Easy Spin stays firmly in place throughout. Now bring the spinner to a quick stop, which also fluffs up your salad. Remove the basket, pour out the dirty water, and voila, your salad is ready. Now let's go back to the dirty water we removed and see what you won't be eating in your salad.
So that's really the same thing. The lettuce is inside the spinner. You pull the crank to, or push, I don't know how it works, but whatever, you make it spin. The wet salad spins around and around and the water goes out the holes because there's nothing pushing the water inwards. So the water goes out the holes in a straight line. The lettuce gets pushed inwards. So I'm not even going to write this one out, but the answer would be the lettuce, the walls of the spinner push the lettuce inward. All right, moon orbiting the Earth. There's no video for this one. Why doesn't the moon go flying away? You know this. The Earth, or the Earth's gravity, pulls the moon inward, right? If the Earth's gravity suddenly disappeared, the moon would float away, right? Okay. All right, a kid on a merry-go-round. So you should be picturing, big disc with a kid sitting on it. And there's probably some sort of handle or something that he hangs on to, right? And it spins around and around. Okay, and so the idea is he wants to go off in a straight line, but he doesn't because he's holding onto the handlebars. So the idea is he's pulling the handlebars outwards, and Newton's third law tells us there's a reaction. The handles pull the kid inward, right? All right, here's one other video. I just thought it was worth sharing. It's kind of funny. I don't think any of these people died. I'll just let you watch.
Не подходи, блядь!
Okay, so in that video, you can see them kind of hanging on for dear life as they used that car to make the merry-go-round spin super fast. Not a great idea. But you can really see them. They're really hanging on, really using those handles to pull themselves inward. All right. Coin on a record. This is an interesting one. If you picture a coin on a record, if the record spins too fast, it's going to slide off. If the record is spinning slowly, it won't slide off. And what prevents it from sliding is friction from the record pushes the coin inward. Okay, and the car on the circular racetrack is the same thing. That imagine getting like onto 696. There's that ramp, and it goes around like this, right? If you hit an ice patch right here, you're not going to go in a circle, right? You're going to drive along, and when you hit the ice patch, you're going to go, right? Not in a circular path, right? So they bank the curve to give you a little bit of inward push, and there's friction, right? If there's no friction, you don't go in a circle. If there is friction, you do. So the friction between your tires and the road is pushing the car inward, okay? So this one's the same thing. Friction from road pushes car inward. All right. So without the video clips, we're at 16 minutes. The video clips are probably going to bump this up. So anyway, there you go. Happy viewing.